We're going to cover sections 3.3 and 3.4 for this lesson. Now, as we go into talking about the truth tables and its negation and talking about the compound statements, and we talked about the connectives in the last section, we're going to now go into truth tables. And we talked about in logic we represent true or false as using a variable P or Q. We're using those variables now. Now what you need to learn, and learn this by heart, there are 4 possible combinations of truth values for P and Q. And what I have here listed, I'm pointing an arrow to it. These are the 4 possible combinations of truth values for P and Q. So you will need to know that for P, we label this as true, true, false, and false. And then for Q, we alternate true and false, beginning with true, false, true, false. Okay, beginning with true. So this is going to be what we called our standard. This is what we're going to use to start off. And I'm going to show you how to construct a truth table as we go through this section. But we're going to also look at the definitions of negation, conjunction, and disjunction. And remember that negation means not, the opposite. So given an example of the negation of not P, we have false, false, true, and true. So these are the words that you're going to see, and its appropriate symbols that you need to understand the meaning behind it. Also, we're going to look at is the conjunction. We talked about conjunction meaning the word and the appropriate symbol. So when it comes to the truth table, keep in mind with conjunction, it says it's true only when both component statements are true. I'm going to put an asterisk here. It's only true when both P and Q are true. And for disjunction, we said it was the letter V. And for a disjunction, it says it's false only when both component statements are false. And remember, with disjunction, it says at least one must be true. So if one must be true, then whenever you have 2 false for P and Q, then it makes the whole statement false. So let's look at the following examples. Example 1, it says, let P and Q represent the following statements. P, it says 3 plus 5 is equal to 8. Well, first of all, let me ask you this. Is this a true statement? Yes, it is. So I'm going to put P beside this particular statement. For Q, we have 2 times 7 is equal to 20. Is that true? That would be false. Okay. So what we're going to do now is for P, we're going to represent that with the letter T for true. And for Q, we're going to represent that for F because that statement is false. So we have here, determine the truth value for each statement. We have P and Q. So for P, we said it's true. And then for we have Q, we said that it was false. Now remember, for and, it says for the conjunction, it says both P and Q must be true for this statement to be true. So my question to you is this a true value? No, it's false because both P and Q must be true. Let's look at example B. We have P and not Q. P we call T, not Q. Well, initially we called Q false, so not Q, meaning the opposite of false becomes true. So now we have P being true and Q being true. And this is a conjunction. Is this a true statement here? Yes, it's true because both P and Q must be true. C, we have not P or Q. This is a disjunction. And a disjunction means it's false only when both P and Q are false. So let's look at not P. Well, initially P is true, so not P would be false, and Q is false. So is this a true statement? No, it's not. We would say false because both P and Q are false. It makes this whole statement false. And then letter D, we have not P or not Q. Not P, the opposite of P is true, right? Well, right now is P is true. The opposite of true is false. And then not Q, the opposite of false would be true. So we're going to call not Q T. So since this is OR, in order for the statement, a disjunction to be false, both P and Q must be false. And P and Q are not false. So this would be a true statement. Now it says here, next concept, a truth table for a compound statement shows when the statement is true and when it is false. The first few columns show the simple statements that comprise the compound statement and their possible truth values. The final column heading is the given compound statement. The truth values in each column are determined by looking back at the appropriate columns and using one of the 5 definitions of symbolic logic. Now we will be coming back to what is conditional and biconditional. We're not going to talk about that now. Section 3.3, our focus is on negation, conjunction, and disjunction. So now, for example 2, we're going to construct a truth table for, it says not, and in parentheses, P or Q, to determine when the statement is true and when the statement is false. So I'm going to show you how to construct this truth table. Now we're going to start off with the 4 possible combinations. So we're going to start off with P. And like I said, you need to know the 4 possible combinations. We're going to start off with our bar. In P we have T, T, F, and F, true, true, false, and false. And we're going to write Q, true, false, true, false. Now remember what we're going to do first, start off with what's in the parentheses. We're looking at P or Q. And remember, we're going to fill out this truth table here, looking at our P and Q. Remember, for OR, it says that for P or Q to be false, both P and Q must be false. So we have T and T, T or T. This is true. TF, we have, that's true. FT, we have true. Now, notice we have false and false. That makes this disjunction a false statement at this moment. Now, let's fill in the not P or Q. And we're going to look at the 3rd column here, and we're going to take the opposite. So we have false, 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 and the opposite of false is true. So the question says, determine when the statement is true. Let's look at that. When was it true? Let's look at the last row here. I'm going to say therefore. These 3 symbols represent therefore. Not P or Q is true. We'll say when it's true, when both P and Q are false. Go back to your truth table. Okay? And then otherwise, Our other combinations that we have here, not P or Q, is false. Okay. So when it is true, for this particular truth table, when P and Q are false, okay, and then otherwise the truth table ends in a false statement. Now, the last definition I want to talk about here, I'm going to put an arrow to it and underline it, is the word tautology. Tautology, excuse me. It says if a compound statement is always true, it's a tautology.